Hello, everyone, and welcome to another wonderful day of chemistry. So last time we were discussing effective nuclear charge. So this is essentially how much the nucleus wants any given electron. However, this isn't the only major feature describing nuclear attraction, because one of the other problems is that the further away the electron is from the nucleus, the less closely it will interact with the nucleus, because these are going to be the two major determining factors of the attraction of an electron to the corresponding atomic center is how how much of the charge does it feel and how close you are. So this makes it really important that we're aware of electronic radii. So a way to look at this is the average distance of those valence electrons from the nuclei. And it will tend to depend on three key variables. A, the overall principal quantum number, or n. Two, that Z effective charge, because again, the larger the charge, the more attraction and the closer in the electron will be. And three, the angular momentum. So let's go ahead and look at each of these individually. So the major controlling factor is going to be n, because the larger the quantum number, the further out the orbitals are going to be placed. A 2s orbital is further out than a 1s, a 3s more than a 2, and a 4s more than a 3, and so on and so forth. And that's really what we tend to see with this pattern, is hydrogen and helium only occupy the 1s orbital. And then we have this huge jump in distance as we start occupying the 2s orbital for lithium, and then it goes down and then back up as soon as we occupy the 3s, and then down, and then we occupy the 4s, and then down, and over and over. Every time we occupy another electronic shell, the radii immediately jumps up. But then that brings us to the question of why does it decrease? And this is largely due to that increased Z effective. Because as we then go from, say, lithium to beryllium, what ends up happening is we have a lot more nuclear charge. And that nuclear charge will shrink those atomic radii as the nuclei has a much stronger grip on all of the electrons. And that's exactly what we tend to see in this repeating pattern, because the effective nuclear charge increases and all of the electrons spend more time closer and closer in. And we see this pattern repeat over and over. It gets a little bit messy once we hit something like rubidium. And this is once we get to this level, we are now occupying the F subshell. And with F and D character, this tends to see a lot of oscillation in how many of the S orbitals are occupied versus how many of the D and Fs. And this causes a lot of chaos once we hit these larger groups. Which brings us to another key feature, which is we tend to see that as our principal quantum number, or as our angular momentum increases, the average electronic distance will decrease. And that is part of the major feature here. That said, it is worth noting that every atom will contain at least one s valence electron, which will really control the distance of the most far out electrons, which does tend to keep a lot of these comparisons fairly relatable, even when we're dealing with the fact that, say, a 3p orbital on average is going to be much closer in to the nuclei than a 3s. But one of the big things that we tend to see is, especially because of these countervailing effects of the principal quantum number versus effective nuclear charge, we tend to have these rough periodic trends of every time I go across the periodic table, my Z effective grows and the atoms will contract. So the further right on the periodic table you are, the smaller the atoms. However, because of the principal quantum number increasing every time we go down the periodic table, as we go from first shell, second shell, third shell, fourth shell, fifth shell, and sixth shell, we tend to see a big increase in the size as we go further down the periodic table. However, this does lead to some odd features, such as it turns out that radon will have a smaller smaller size than, say, lithium, which feels a little bit awkward. But again, the big key feature is you go up and to the right, you get smaller, down and to the left, you get bigger. It's a little bit hard to try and compare elements on the diagonal this way, as it as it contrasts those general trends. However, one of the big things I do want to emphasize is everything I've talked about so far is the average electronic radii. However, it turns out that when we're talking about the radii, it is kind of a fluid term. So the term I used was pretty good because it talks about where those average valence electrons are. However, when we're talking about molecular interactions, there's much more useful terms of atomic radii. And there's four major ones that tend to be used. The first one that is most commonly used is called the covalent radii. And this is based on the idea of covalent bond distances. So I've got two atoms which contain a covalent bond. So in this case, it would be diatomic sodium. And then I simply say, well, I have a given bond distance in between these two. Well, the covalent radii is simply going to be half that bond distance. And so all you need to do to determine these covalent radii is to measure the diatomic bond distance of any given set of elements, which, while tricky, is fairly doable. The other option, and this tends to be used for our metal systems, not too surprisingly, is the metallic radii. So in this case, what you have to do is generate a solid of the element of interest. So this is typically used for our metal species. And one of the key features of a metallic elements is they'll tend to have slightly larger bond distances as they aren't sharing those electrons quite so intently. And so what you simply do is take a look at the distance in between two identical atoms in a metal lattice, and half that distance is going to be the metallic bond radii. So fairly straightforward. And then the last one has to do with what if the elements aren't bonded at all? So in this case, you can imagine something like a noble gas, where I go ahead and I compress my gas so that all of my elements are independent and non-bonded. Well, in this case, then I look at the distance in between two non-bonded elements as tightly packed as I can make them. And then half that distance is going to be my van der Waals radii. So again, all three of these distances are related to essentially half the distance in between a homonuclear connection, whether the electrons are being covalently shared, essentially passed back and forth like it's a metal, or essentially not shared at all and simply pressed together. But again, all of these rely on that homonuclear connection. However, there is another major way that we tend to see atoms arranged, and that's in ions. So when I'm dealing with ionic species, trying to determine their radii is a little bit more messy because I can't exactly get diatomic sodium cations because the positive charges will repulse. So what I need to do is essentially take a cation-anion pair and measure the distances in between the two metal centers. Now, what we then need to do is have a reference distance. So if I know the radii of one of my two species, I should be able to determine the radii of the other one simply by taking the difference of the of the total distance and the known species. And these are usually determined using a basis either of the oxide or fluoride bond distance, and then you can back out the cationic distances. And once you have a couple cation distances known, you can get the rest of your anions like chloride. However, one of the things that should be emphasized is that the ionic radii are not going to be the same as the covalent or electronic radii. So let's go ahead and compare the ionic radii versus the covalent radii. So for cations, what we tend to see is that the radii will shrink as we removed a valence electron. So I go from occupying a 3s shell to only having 2p electrons. So not too surprisingly, the size of the molecule practically falls in half. And we see something very similar with magnesium, and so on and so forth as I go across the periodic table. We see these drastic decreases in molecular size. And this is going to be much more pronounced for molecules where we completely empty a valence shell, such as sodium, magnesium, and aluminum, where all I'm left with is essentially a core of noble gas-like character. This will be a little bit less pronounced if I'm talking about a species that leaves, say, a single s electron behind, like if I was only had aluminum 1+ or 2+. But most of the time when we're talking about cationic species, we've completely emptied our valence shell, which causes this drastic decrease in size. However, this leaves half of the story untold. We also have our anions. And here's the tricky part about the anions. The size of these ions will actually increase because I'm adding in additional electrons. And as I add in those additional electrons, I add in additional electronic screening, which means that all of the electrons already there feel the nuclear charge a little bit less, and they'll balloon out. And you can kind of see this as a general sort of pattern. So for example, when we're talking about a lot of our alkali and alkali earth metals, they tend to see almost a 50% reduction in size. So it's a huge decrease. In comparison, when I'm looking at species like nitrogen and oxygen, you put in 2 or 3 electrons in there, they practically double in size. So we get some big differences in between our metals, which all tend to lose electrons and thus decrease in size upon ionization, and our nonmetals, which are more electronegative, like to gain electrons and will increase in size. And this is one of the key trends of the periodic table: species that lose electrons versus those that gain electrons. So next time, we'll go ahead and look a little bit more into forming our ionic species and figuring out exactly how much energy that takes. Until then, take care.